So, we're back again. We're still talking about body defences. Okay? We have talked about pathogens. We've talked about the way pathogens get into the body. We have just talked about how we basically stop some of those pathogens from getting in. This one is specifically about non-specific body defences. These defence systems are designed to stop any type of pathogen getting into your body. Doesn't matter if it's a virus, or if it's a bacteria, or if it's a protozoa, they're designed to try and stop everything from getting into your body. The next session that we do, we'll cover what the hell happens if these defences are breached and a pathogen does get into the body, okay, through one of those 4 portals of entry. So in this session we're going to look at 2 of our most important non-specific, sometimes called innate, body defences. Major ones. Number 1, numero uno, your skin. Your skin is a major body defence. And secondly, we'll look at mucous membranes. Mucous membranes are again a major barrier to pathogens getting into the body. So we will look at the skin and we will look at mucous membranes. Sounds fun? Say sounds fun, Dave?
Sounds fun, Dave.
Oh, right, that does sound so energetic. So let's have a quick look at our non-specific body defences. Your non-specific body defences, if you think of the skin, I want you to kind of think of a castle. Okay? How is a castle good at what it does? Why is a castle a fantastic piece of Norman, because they weren't very often built by the Normans, a fantastic piece of Norman engineering? What is it about a castle that stops invaders getting in?
4 walls around it, please.
Walls. What can you tell me about the walls? They are barriers. They are, did somebody say strong? Strong.
No.
What is it? If you look at a castle wall, is it thin or thick?
Can't absorb anything.
Say again, sorry, Miss One.
I just said we can't absorb anything.
Can't absorb anything. So basically, really, really thick, really strong, thick barriers. Your skin is kind of that. Your skin is kind of like a castle wall. We'll look at that in a bit more detail. Here's our lovely castle wall. Here is a profile of your skin. Now, the bit that we're interested in, this is where sometimes students go wrong. So let me give you a word of warning right now. There is a shed load of stuff written about the skin. I am not interested in all of the stuff about the skin other than one single layer. The very outermost layer of your skin. This is the barrier that prevents pathogens from getting in. So when you're doing the assignment for me and you're talking about the skin, I don't want to know about the dermis and I don't want to know about stuff down beneath. I just want to know about the outermost layer of the skin. So don't spend any time talking about the deeper layers of the skin, just the outermost layer. Here is your skin. This is your scalp. And your scalp is literally crawling with bacteria. Literally. Right now, they are literally thousands of bacteria all over your scalp. All moving slightly and dividing all the time. Like tiny, teeny, weeny little caterpillars mooching around all over your skin. And we have a reaction from those people at the back. Okay. So, the first, the largest, the most important body, non-specific body defense is the skin. The skin we often call a cutaneous membrane. But the bit that we are really interested in when we look at the skin is this very outermost layer that we call the striatum. Striatum means a layer. Corneum. Corneum. Striatum corneum. Now, for those of you who indulge in spending thousands of pounds over the course of a year on creams that are designed to improve your glow and improve your plumpiness and improve your texture. Okay? I am about to dispel all of those myths right now.
They're not good for your skin, are they?
And I'll come to that one because you were in part right. Because the outer layer of your skin is completely, utterly, absolutely, no way dead. The outer maybe 15 to 20 layers of your skin are nothing more than dead cells that have been compressed to look like pancakes and are completely and utterly deceased. They live no more. They are completely and utterly dead. These outer layer of cells, guys, these outer layer of cells are called corneocytes. They're called corneocytes, and they is dead. Flat and dead. Okay? But what they do, bad English, just like a castle wall, is that these 15 to 20 layers are quite thick. They're quite thick, and they present to the outside world an impassable barrier, so that pathogens cannot get into your body unless they have a break in that layer. As long as there's not a break in that layer, then effectively pathogens will not get into your body through the skin. In other words, one of the portals of entry that we talked about previously, they will not be able to use that portal if your skin is intact. Which begs the question, why is it that people put on a face mask that biologically peels off the outer layer of your castle wall, all in the sake of improved beauty? Why would you demolish the outer layer of your castle wall by having a dermological peel, which literally reduces your castle wall from 15 to basically maybe 2? Why would you do that? Why would you do that? Because at the end of the day, guys, big shocker alert for you, sorry, spoiler alert, you are constantly shedding the outer layer of your skin anyway. What do you think house dust actually is? It's you. House dust is effectively bits of you that have settled on furniture because you are constantly, here we go, spread the love. You are constantly spreading skin everywhere. Everywhere you go, you leave skin behind you. It's designed to come off. It's actually designed to come off. So why is that good? Why is that a good thing? Brilliant. It's a brilliant concept, this. Because as those corneocytes come off your skin, anything that is stuck to them comes off with them. So the bacteria that were living on those corneocytes on your skin, when that skin cell comes off, the bacteria leave with you. So basically they're constantly leaving you because your skin is constantly being shed. Desiccation also dries them out. So because you've got this incredible barrier, when your skin starts to dry out, like now, it's not wet, all those bacteria that are on the surface of your skin, they will simply dry out. It's almost like leaving a prune out on the surface of a workbench. It's going to just dry up. So we basically lose pathogens because of desiccation, they dry out, or what we call desquamination, because your skin naturally peels off itself. Your skin naturally peels all the time. So desquamination is basically as the skin peels, the bacteria leave with it for free. You don't need to put a peeler on it. It basically just goes for free. Okay? And it carries all of those bacteria away with it. It is super impressive. Super impressive. Everybody okay, guys, with that concept? Everybody okay? say yes, Dave?
Yes, Dave.
Thank you. Now, the problem is that you, as a human being, do not have skin all over your body. Now, that may come as a bit of a shocker to you, but you do not have this thick skin all over your body. Most of you is covered in this stuff, but there are certain areas that are not covered by this thick skin. Those areas that are not covered by thick skin, we protect by using what we call mucous membranes. Mucous membranes. And mucus is actually snot, but mucus is also something that we use to protect ourselves from pathogens. So anything that is not covered in skin is covered in what we call mucous membranes. Mucous membranes. Where the hell do we find these mucous membranes? Well, we find them in your mouth, your nose, your sinuses, your throat, your lungs, your gastrointestinal tract. These are all areas that are not covered in that protective striatum corneum layer. In other words, these are all areas, including eyes, that are not covered in what you would say is skin. Anything that's not covered in skin is covered in a mucous membrane. How the hell do these mucous membranes work? They have two parts to them. How many parts?
Two.
How many parts?
Two.
Thank you. Can anybody say it in French? Good. Thank you very much. Anybody say it in German?
Dry.
That's three. Zwei. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. Anybody count to 10 in French?
1, 2, 3, 4, 5, 6, 7, 8.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Anybody do it in Latin? No. Anybody do it in Greek?
No.
No, neither do I. Anyway. There we go.
Okay.
Okay, guys, back to me. If we're going to talk snot, guys, if we're going to talk snot, let's talk goblet cells. Goblet cells. Goblet cells are snot factories, because that's what they make, snot. Why do we call them goblet cells? Because when we first looked at them under the microscope, somebody actually thought that these cells look like a goblet. Don't ask me why, don't ask me why, don't ask me why. Because when we look at them in greater detail, they kind of don't look like a goblet at all. A goblet is a drinking vessel, so we know like a wine glass. Oh, there we go. Yeah, so a glass that looks like, as opposed to one that looks like that, with froth on the top, with IPA in it. Now, you will also notice on here there are different types of cells. So some of these cells produce snot, which is this one. This is a goblet cell. And some of these cells don't produce snot, but can you see that they've got little hair on the top? Little short hairs on the top. We call these little short hairs cilia. And these are called ciliated cells. Okay. So when we're talking about our mucous membranes are made up of cells that produce snot, which are goblet cells, and ciliated cells. And we'll talk about... So say again, Chloe?
The bottom one, not the ciliated one.
This one?
No.
This one?
Ciliated cells.
Ciliated cell.
Ciliated.
It's not just hairy bits, it's down there.
They've got little hairs on the top.
Not just the hairy bits.
Like mine, little tiny hairs on the top of them. So they're like me, so I stand there with little hairs on the top. Only these little hairs move. Mine's too short now, so I move sometimes. Okay. So here's a little view for you guys, here's a little view. These are our ciliated cells looking down on them. All these little balls here are bacteria. And all this white stuff, can you see all this white stuff? That's snot. That's mucus that you've made. Well done. So, This is kind of an important slide. This thing that talks about what we call the mucociliary escalator. An important slide. I want to make sure that you concentrate on this one, because this is something that I would expect to see in your report. The mucociliary escalator. What the hell is it, Dave? Well, I'll tell you. The mucociliary escalator, okay, what does an escalator do? Moves things, doesn't it? If you stand on an escalator and John Lewis, it kind of moves you, doesn't it? Right? Now, the mucociliary escalator, guys, only ever moves things in one direction. Do you think it moves things into your body, or do you think it moves these things out? Correct. So the mucociliary escalator is designed to move things out of your body. Okay. So what we have are these wonderful ciliated cells, and we have these goblet cells. The goblet cells produce snot. What do you think snot actually does to bacteria?
Coats it so you can't get anywhere else.
Yeah, it literally coats them, clumps them together, so they can't really move around. It literally just sticks them together. Then these ciliated cells waft like a Mexican wave and literally waft them out of your body. They literally move them back out of your body. So inside your lungs, for example, the passageway down your throat that goes into your lungs, you have these ciliated cells and goblet cells. And these ciliated cells and goblet cells literally waft out, the ciliated cells waft out any bacteria that you've breathed in. The bacteria get covered in snot, which means the ciliated cells literally just waft the snot and the bacteria back up and back up and back up. And eventually, you will either do one of two things. You will either A, swallow it, which is what you do when you're asleep. You swallow your snot when you're asleep, because these things carry on going even when you're lying down. Or you will swallow it like that, or you will cough it out. Either way, what you are doing is getting rid of it. Now, does anybody ever wonder why it is your nose runs when it's cold outside?
Because your body's warm.
No,
Because you're releasing bacteria.
not quite. You're getting closer.
Is it the temperature?
It is to do with the temperature thing. When it is really cold, those ciliated cells don't work as well, which means that all that mucus that you are producing starts to run out of your nose. So ciliated cells kind of don't work as well when it's freezing cold, which is why your nose runs. Ciliated cells don't work as well when you are a smoker. For those smokers in the room.
Why look at me?
For those people who smoke, the smoke paralyzes the ciliated cells, which means all the bacteria start to fall into your lungs. What does a smoker do first thing in the morning, apart from light up another cigarette? Cough. And why do you think they are coughing? Because they are expelling all of the mucus that's actually gone down, because those ciliated cells have been frozen by the nicotine. So a smoker's cough is basically the fact that all the stuff that should have been coming out has actually gone down the wrong way. Now, most of the time, that's not going to be a major problem. But if it becomes problematic, then you could end up with things like pneumonia, because you are now filling your lungs with bacteria that you do not want down there. Okay? You don't want down there. So, effectively, we've just talked about the mucociliary escalator. So that previous slide and this slide are super important slides. That previous slide and this slide are super important slides because they talk about the benefit of the mucociliary escalator. The fact that we have these ciliated hairs that basically waft everything out of your body. And they beat in this incredibly well-organised manner, wafting all of that material that you have breathed in out of your body. If you swallow the bacteria as they are wafted up from out of your lungs, basically those bacteria fall into your stomach acid and they are destroyed. Because not many bacteria can live in the acidity of your stomach. So they become destroyed by it. That mucociliary escalator, guys, is incredibly efficient at what it does, because it can remove things that are 0.003 of a millimetre, which means they can remove virtually all bacteria that have got into your lungs. And by the way, you are breathing in thousands of bacteria a day, and they will be removed for you by this process. So we had a question.
So, for example, if a child sniffs rather than blowing a nose,
Yes.
Can that bacteria be reintroduced, or because it's already stuck to the mucus,
Yes.
can it not?
Yes, it can be. Which is why it's always a great idea. That's a very good question. It's always a great idea. Same thing. Catch it. What was it? Catch it.
Kill it, bin it.
Catch it, kill it, and bin it. Blow your nose. Don't keep on sniffing all the time. All the time. So basically, yeah, you can. It's a great way of doing it. And in terms of children, again, because they might wipe the nose, they're basically just reinfecting themselves all the time. But it's brilliant at what it does. The mucociliary escalator is absolutely brilliant at what it does. It protects you where you have not got that layer of skin. Is that clear for everybody? How it works? That's super important. That's great. Just to finish off with, there are a couple of other areas that are non-specific and protect your body. Just want to talk about this word, lysozymes. We find lysozymes in mucus. We also find lysozymes in tears and also in saliva. Lysozymes are enzymes that will break down bacterial cell walls. If you break down a bacterial cell wall, you destroy the bacteria. So these things are super important. So you can kind of think of lysozymes basically strip the armour off the bacteria. No armour, no protection, which means they will die very, very quickly. So lysozymes are really good at breaking down bacteria so that they basically die very, very quickly. People happy with that concept? Lysozymes produced in your saliva, produced in your skin ducts, or produced in mucous membranes, break down bacteria for free. So every time you are bathing your eyes in tears, not crying, but just bathing your eyes in tears, you are destroying all the bacteria that stick to your eyes. Because tears have within it that lysozyme enzyme which breaks everything down. So let's recap. We have got, in our first line of defence, we have got skin, we have got mucous membranes, and we have got tears. We know everything now about that striatum corneum, that outer layer of skin, which has got around about 15 to 30 layers of those corneocyte cells, all designed to basically stop bacteria getting in. The bacteria either dry on the surface, desiccation, or are dislodged when your skin comes off, desquamination. You also have secretions from your body, like lysozyme and enzyme, which will destroy bacterial cell walls. Brilliant. You kill the bacterial cell walls, you kill the bacteria. And we find those lysozyme enzymes in mucous membranes and also in tears as well. Finally, one which we basically very briefly touched on, which was stomach acid. That mucociliary escalator takes everything from your lungs, or going down into your lungs, and takes it back into your throat where you can swallow it. Once you swallow your snot, it lands in acid, and the acid will kill the bacteria. Whatever it takes, You are protected. Wake up.